Welcome to this session on the stiffness matrix. In this session, we'll be taking everything we've developed so far, the global stiffness matrix and the force vector, and we will be solving the stiffness equation, finally finding out what those displacements are. By the end of this session, you'll understand how everything that we've built so far feeds into solving the displacements, and you'll also be able to code it. Here's a quick reminder of where we are in the broader stiffness method process. We've already derived the element stiffness, assembled the global matrix, and developed the load vector. Today, we focus on solving for displacements. This is the heart of the method, before we then move on to reactions and internal forces. This flow mirrors how a full-time finite element analysis proceeds, from local elements to the full global picture, and then from the global motion back to the local response. As we already know, the stiffness method is based on the fundamental equation K times D equals F. The global stiffness matrix represents the stiffness of the structure, or how resistant the structure is to deformation. The displacement vector contains the unknown nodal displacements, and the load vector contains the external forces applied at the nodes. Our aim is to solve this equation for D. Solving this single equation bridges our mathematical model and the physical reality of the structural behavior. Before solving the structure, we must apply boundary conditions. These come directly from the supports. Each support type restricts certain degrees of freedom. A fixed support restrains all movement and rotation. A pinned support prevents translation in both perpendicular directions but allows free rotation. And a roller support restrains translation in only one direction while allowing movement and rotation in the others. These restraints are applied by setting the corresponding displacements in our displacement vector d to 0. The boundary conditions define how the structure interacts with its surroundings and ensures that the analytical model behaves exactly like the real structure. Once the restrained degrees of freedom are known, we can remove the corresponding rows and columns from the stiffness matrix and the same entries from the load vector. This gives the reduced system KFF-DF-FF, which contains only the unknown free displacements. The reduced matrix is smaller, symmetric, and well-conditioned, ready for direct solution. Physically, this step isolates the active parts of the structure that are free to move, and we'll see exactly how to do that in our example further on. The reduced system is a set of simultaneous linear equations linking forces and displacements at the free degrees of freedom. Solving it gives the unknown nodal displacements at all free degrees of freedom. Each value in df tells us how a node moves under the applied loads. In theory, this is simply a matter of linear algebra. Physically, it represents how each node moves under the applied loads. After solving the reduced stiffness equation, we can reconstruct the full displacement vector for the entire structure. This is done by placing the solved free displacements back into their correct global positions and assigning 0 values to the restrained degrees of freedom. The resulting vector contains every displacement and rotation in the structure, expressed consistently in the global coordinate system. This complete displacement field represents the overall deformation of the structure under load and provides the basis for calculating the support reactions and the internal forces in the following steps. Each displacement value now has a clear physical meaning. Translations are measured in units of length, in our examples in meters. Rotations are measured in radians, and all directions follow the global axes. Even though these movements are usually very small, they reveal the flexibility of the structure and how the loads are distributed. Understanding this step helps connect the numerical results with a visual picture of the deflected beam or swaying frame. Once we obtain displacements, it is essential to check that the model is both stable and consistent. The stiffness matrix should be symmetric and positive definite, and the supports must eliminate any rigid body motion. Checking equilibrium means that the applied loads are balanced by the structural reactions, and it confirms that the numerical solution represents a physically realistic system. Let's now apply the full procedure to our portal frame example. The frame carries a uniformly distributed load of 10 kilonewtons per meters on the top beam and a 20 kilonewton point load acting downwards at node 3. The supports are at the bases: a pin support at node 1 on the left and a roller at node 4 on the right. The columns and beam each have a square cross-section of 200 millimeters and a modulus of elasticity of 200 gigapascals. With the stiffness matrix and load vector already assembled in our previous examples, we can solve the reduced system to find the displacements. This example demonstrates the complete workflow in which we'll determine the nodal displacements by solving the reduced stiffness equation. As we discussed earlier, each node of a 2D frame has 3 degrees of freedom, horizontal and vertical translations, and a rotation. With 4 nodes, the structure has 12 total degrees of freedom. The supports restrain U1, V1, and V4, leaving 9 free degrees of freedom to be solved. Using the same procedure as before, we assemble the global stiffness matrix for the frame. Each element's local matrix is rotated into the global coordinates and then assembled according to connectivity. The result is this 12 by 12 matrix in units of 10 to the power of 7, which captures the coupling between all nodal degrees of freedom. Before solving, we apply boundary conditions and external loads. The boundary conditions, or restraints, come from the supports. At node 1, which is pinned, U1 equals V1 equals 0. And at node 4, which is a roller, V4 equals 0. And we can place this in the displacement vector as zeros, because there will be no movement there. The force vector, which we developed previously, includes the 10 kN per meter UDL on the beam and the 20 kN point load at node 3. These loads act in the global coordinate system and feed directly into the stiffness equation. The global equilibrium equation for the full system is F equals K times D. At this stage, it contains both the restrained and free degrees of freedom. We will next apply the support conditions to eliminate the restrained degrees of freedom. We now apply the support conditions to reduce the global system. By removing the restrained degrees of freedom, the rows and columns for degrees of freedom 1, 2, and 11, we obtain 9 equations for 9 unknowns. The reduced matrix captures the essential behavior of the frame while ensuring numerical stability and correct physical constraints. The remaining submatrix KFF relates the free degrees of freedom only, and the corresponding load vector is FF. We can now solve the reduced system KFF times DF equals FF. After applying supports and loads, we arrive at the reduced stiffness system KFF times DF equals FF. This only contains the 9 free degrees of freedom. Solving this system gives us the displacements and rotations of the unconstrained nodes. Solving the reduced equation yields the free displacement vector dF. These values represent the movements and rotations of each unconstrained node under the applied loads. As expected for a stiff steel frame, the magnitudes are small but define the overall deformation behavior precisely. Once dF is known, we can rebuild the full global displacement vector d. The solved free displacements are inserted into their correct global positions, and the restrained degrees of freedom are set to 0. This ensures every node is represented in global coordinates and prepares us to compute the support reactions and internal forces next. The computed displacements can now be interpreted in physical terms. The top beam deflects downwards under the uniformly distributed load, with a slightly larger deflection near node 3, where the 20 kN point load acts. Because the left base is pinned and the right base is a roller, the frame also experiences a small horizontal sway to the right. Both columns bend accordingly and produce the characteristic portal frame deformation with downward beam curvature and outward column rotation. This global deformation pattern is fully defined by the displacement vector d and forms the basis for calculating reactions and internal member forces next. So, to summarize, the process involves assembling the global stiffness and load matrices, applying boundary conditions, forming the reduced system, solving for free displacements, and then reconstructing the full displacement vector. We can then interpret the results. These steps complete the theoretical solution of the stiffness method for displacements and prepare us to determine support reactions and internal forces. Having established the full theoretical basis, the next bit turns to the implementation. Here, we're going to translate the procedure into a short MATLAB or Octave script using the same frame example. The goal, as we've mentioned before, is not to become programmers, but to understand how each theoretical step corresponds to a line of code, bridging the gap between the structural theory and computational practice. We will just have a quick look through what we've coded in previous lectures, and we'll focus here on the final step, solving the stiffness equation and finding displacements. If you'd like a full line-by-line explanation for previous steps, you can review them in the earlier coding sessions. We start by clearing the workspace and setting everything in SI units. This ensures a clean and consistent setup for the analysis. We define the node coordinates and the element connectivity. Here we describe the material properties E, A, and I based on the properties provided in the input. Now that we know the coordinates and connectivity of the structure, we can compute the geometry of each element. Here we calculate the element lengths and orientations, which we'll use later in the stiffness transformation. Here I've left the degrees and radians, and I'll only convert them to degrees later for reporting. Now that we know the geometry and properties of each element, we can calculate the local stiffness matrix for each member. We will then rotate each element's stiffness matrix to align with the global coordinate system so that all the elements are expressed consistently. And now that each element's stiffness is in global coordinates, we can combine them into one system matrix for the whole frame. The next step is to build the global force vector F, which we just did in the previous lecture. And this contains all the external loads acting on the structure. The program is set up to handle two kinds of loading: direct nodal loads and uniformly distributed loads, or UDLs, on the elements. Here we calculate all the nodal forces and place them in the correct locations in the force vector. And in our example, it looks like this: the 20 kilonewtons acting vertically downwards at node 3. And in this part, we assemble the uniformly distributed loads. These are rotated into the global coordinate system and added to the force vector in the correct locations. And this leads to the following final force vector for this example, including both the UDL and the point load at node 3. Now to the new bit. So, now that our global stiffness matrix K and the load vector F are assembled, we need to apply the boundary conditions and solve the stiffness equation to find the nodal displacements. We need to begin by identifying which degrees of freedom are restrained by the supports. As we know, each support limits certain movements, so fixed support would prevent all the translation and rotation at that node. A pin support would prevent all horizontal and vertical movement, but would allow rotation at the node, and a roller support restrains movement in one direction only, while permitting movement in the perpendicular direction and rotation at the node. In our portal frame, node 1 is a pin, so both horizontal and vertical displacements are fixed, so U1 equals 0 and V1 equals 0. Node 4 is a roller, which only restrains the vertical motion, so V4 equals 0. All rotations in these supports remain free. Here we will define those restraints using the mapping matrix N, which will store the global numbering of every degree of freedom. Each node has 3 degrees of freedom: horizontal U, vertical V, and rotation theta. So N11 refers to U1, node 1 degree of freedom 1. N12 refers to V1, so that is node 1 degree of freedom 2. And N42 refers to V4, so node 4 degree of freedom 2. We combine these into one line called fixed DOFs. So you can see here fixed, I've got N11, N12, N42. And this gives us the global indices 1, 2, and 11, which represent the restrained movements in the structure. Next, we will list all degrees of freedom and identify the free ones. In free DOFs, where we can see set diff from all DOFs to fixed DOFs, this command removes the restrained degrees of freedom from the total set, leaving only those that can move under the load. Once we've defined the boundary conditions, we can reduce the global system to include only the free degrees of freedom. So essentially, KFF times DF equals FF, where, as we already discussed, KFF and FF are the stiffness matrix and load vector corresponding to the free degrees of freedom. We can solve this reduced system using MATLAB's backslash operator. So you can see here that DF equals KFF backslash FF. The backslash solves the system directly without computing the matrix inverse. So it's faster, more accurate, and numerically stable, especially for larger systems. And finally, we rebuild the full displacement vector for the entire frame. So d equals zeros in the size of end-off, and d free doffs equals df. This reinserts the solved free displacements into their correct global positions, while all restrained degrees of freedom remain 0. The resulting vector now shows how every node in the structure moves, forming the foundation for the next step, which will be calculating support reactions and internal forces. At the end of the program, we display the main results to verify that the analysis has been assembled and solved correctly. The display format is changed to engineering notation so that values appear convenient. We first print the global stiffness matrix, followed by the element lengths and angles. The angles are converted from radians to degrees for easier interpretation, measured counterclockwise from the global plus x-axis. Next, we display the global load vector to confirm that all applied loads have been included as expected. And finally, we show the global displacement vector d, which contains the computed movements of every node. In our case, translations are given in meters and rotations in radians, with zeros appearing at the restrained supports and small non-zero values at the free nodes. Translations are given in our case in meters and rotations in radians, with zeros appearing at the restrained supports. This output confirms that the structure deforms as expected under the applied loads, a crucial final check before we can move on to reactions and internal forces, which we'll discuss in the next session. Although we've shown this code in MATLAB, it will run directly in Octave as well, which is a free open source alternative. Octave uses almost exactly the same syntax as MATLAB, so you can just copy-paste this script and it'll work without changes. This means that you don't need a paid MATLAB license to practice. Octave is available to download and use at no cost, and this makes the stiffness method coding exercises fully accessible whether you have MATLAB installed or not, so no excuses. In this session, we applied boundary conditions and we solved the stiffness equation, finding the displacements. The displacements fully describe how the structure moves and will form the basis for finding the reactions and internal forces for each member. So join me for next session where we do just that.